Welcome back. So this unit is studying trigonometry. And I know that's a scary word, but all it means is the study of triangles. Trig just is kind of, yeah. So ancient Egyptians and Babylonians started noticing that similar triangles, you had sides that always were in the same ratio. For example, 3, 4, 5 was always a right triangle. And you can even scale it up and have a 6, 8, 10, 30, 40, 50, 150, 200, 250. So they're always in the same proportion. This side to this side would be 3 to 5. 6 to 10 would still reduce to 3 to 5. 30 to 50 would still reduce to 3 to 5. So it was actually the Greeks who came up with the idea of angles and names for those ratios of sides. So consider we have a right triangle, and we use this Greek letter theta to represent angles a lot of times. So just know that that's a kind of like an O with a line through it, and it just means theta. And if we specify the sides as opposite, so across from the angle, adjacent, touching the angle, and the hypotenuse is always the one across from the right angle. If we label the sides like this, they came up with names for all of these ratios. So sine, this is actually sine, S-I-N-E. It's just abbreviated S-I-N. We do not sin in math. Is the opposite side over the hypotenuse. So if I was using this angle, that would be 3 over 5. Cosine would be the adjacent side over the hypotenuse. Tangent is the opposite over the adjacent. Now we also have reciprocals of each of these. Those are cosecant, secant, and cotangent. Notice that sine is opposite over hypotenuse. Cosecant is the reciprocal of sine. It's just the same thing flipped. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. So let's say I have, I know that the sine of some angle A is 5 over 13. And I'm being asked to find the other sides. So let's first draw what we're given. So I'm going to have a right triangle. And I'm going to label this side angle A. So if I'm calling this angle A, then the side across from it is the opposite. Hypotenuse is always across from the right angle. Adjacent is always touching that angle. So opposite, sine is opposite over hypotenuse. So sine of A is 5 over 13. That means this is the opposite side over the hypotenuse. So that means this side is 5 and the hypotenuse is 13. Well, if we're going to find all these other ratios, we also need to make sure we have all the sides. So one nice thing about right triangles is Pythagorean theorem always works. Opposite, I'll make that A. The one I don't know. And I get that B is 12. Now normally if we took the square root, we would have a positive or a negative, but our side lengths are always positive numbers. So I get that the adjacent side is 12. So 5, 12, and 13. So sine was 5 over 13. Cosine is adjacent over hypotenuse. So the adjacent is 12 over 13. Tangent is opposite over adjacent. So opposite over adjacent. Now we're also going to fill in all the others. So cosecant is the reciprocal of sine. In other words, I'm just going to flip it. Secant is the reciprocal of cosine. In other words, I'm just going to flip it. And cotangent is the reciprocal of tangent. So these trig functions, we call them functions, are just giving us ratios of sides. Now we do have some special triangles that I want to talk about because they pop up so much, and also they're going to have the same ratios every time. So let's look at a 45-45, 90. Well, in a 45-45, since this is an isosceles triangle, then these sides are always going to be the same. Okay, so let's say this side was 5. Then this side is also 5. To find that other side, now you may remember the rule from your geometry class. If you don't, then let's come off to the side and do 5 squared plus 5 squared equals c squared, because that's my hypotenuse. 25 plus 25. So 50 equals c squared. C is the square root of 50, which is going to be 5 root 2. So a 45-45-90 ends up with this really special pattern. They're always going to be in the same ratio. So 5, 5, 5 root 2. 7, 7, 7 root 2. If we knew this side and it was a whole number, well, to get there, we would have multiplied by the square root of 2. So to go backwards, we could divide by the square root of 2. So this little side, I'll call it x, would be 10 divided by the square root of 2. And if you do that in your calculator, or if you remember, you can multiply the top and the bottom by the square root of 2 and get 10 square root of 2 divided by 2, or 5 square root of 2. Now, it really doesn't matter which one I choose. They're going to come out to be the same ratio, right? So I'm going to pick one of these, and we're going to do the sine of 45 degrees. So opposite, I'm actually use this one, opposite over hypotenuse. So 5 square root of 2 over 10 reduces to square root of 2 over 2. Cosine. Well, adjacent would still be 5 square root of 2. Tangent is opposite over adjacent. Well, that's kind of a nice one. Now, the cosecant, we would just flip it. And so forth. Now, the next special triangle that we want to remember from geometry is a 30, 60, 90. And I always like to show where this one came from. So it comes from an isosceles. In an isosceles, not isosceles, equilateral, all the sides are the same and all the angles are 60 degrees. If I split this straight down the middle, what it does is it splits it into 2 right triangles, each with 30, 60, 90. Now notice what's interesting about this. Let's pretend like this side was 10. and this side is 10. Well, this little side right here would be a 5, because the whole thing would be 10, and this little side would be a 5. Could we figure out how long that other side is, which would be the height of this equilateral? Well, we could. This side is 5, the hypotenuse is 10, so a squared plus b squared equals c squared. 5 squared plus b squared equals 10 squared. So b is the square root of 75, which is 5 square root of 3. So this side is 5 square root of 3. So notice we kind of get a little pattern there. 5 square root of 3, 10. So if this side was 7, the one across from the 60 would be 7 square root of 3, and the hypotenuse would be 4. If this side was 8, I would get 8 square root of 3 and 16. 1 square root of 3, so 1 times the square root of 3, and 2. Always in the same ratio. So let's look at 30 degrees. If I found the sine of 30, so here's 30, 30, 30. It doesn't matter which triangle I choose, opposite over hypotenuse, opposite over hypotenuse, opposite over hypotenuse, 1 over 2, 8 over 16, 7 over 14. It's going to be the same ratio every time. Cosine of 30 degrees, square root of 3 over 2. And tangent would be 1 over the square root of 3. Or that actually simplifies the square root of 3 over 3, but whichever way is fine with me. Now cosecant is just flipped. So flip of sine, flip of cosine, and flip of tangent. Next, let's look at 60 degrees. 60 degrees, 60 degrees, 60 degrees. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Notice that we get a little bit, they're the same ratios, just kind of changed a little bit because we're using the same triangle. It's still the same triangle, 30, 60, 90. It just depends on which angle you're viewing from. All right. So the other thing we can do with these trig functions is use them to find other information. And what we mean by that is finding missing sides or missing angles, that type of thing, just by knowing at least one side and one angle. So what I want to do in this one is find all the missing sides and missing angles. Well, missing angles are easy because it's always going to add up to 180. If I know that this is 30 degrees and this one would be 60 degrees. Now, I'm going to pretend like I don't remember the rules we just reviewed and use the fact that that's a 30-degree angle. And first, I want to find, let's find side A. So notice I can't use Pythagorean theorem because I only know one side. Well, side A, if I'm using that 30 degrees, this would be considered the opposite, and this would be the hypotenuse, if I'm using the 30 degrees, which I'm going to because it's the one that was given to me. So opposite would be A, hypotenuse is 12, so opposite over hypotenuse is sine. So sine of 30 degrees equals opposite over hypotenuse. Now I'm going to pretend like we don't know what that's going to be. I kind of know, but sine of 30 degrees. Now sometimes it comes out as an ugly number, but I'm going to go ahead and tell you that in our calculator, sine of 30 comes out really nice. We just looked at it. But first, since we're dealing with degrees, we always need to go into the settings and make sure that the angle measure says degrees. So I do have degrees there. And if I press sine of 30, that is actually a good number. It's 1/2. So sine of 30 is 1/2. So 1/2 equals A divided by 12. Multiply both sides by 12, so A is 6. Now from here, I could use Pythagorean theorem to find B. But I'm going to play devil's advocate and use cosine. So cosine of 30 equals B over 12, adjacent over hypotenuse. Now I could multiply both sides by 12 right here, so I only have to do one step in the calculator. Now I could have found what cosine of 30 is first, or I can do 12 times cosine of 30. And notice every time I hit sine or cosine, it automatically opens the parentheses. It needs an angle. And B is 6 square root of 3. Let's practice with a few more of these. So I have this angle, 61 degrees. I'm looking for X. So let's label everything. Here's the right angle. This is the hypotenuse. And the side I know is opposite. So opposite and hypotenuse is sine. So sine of 61 equals opposite over hypotenuse. Now on this one, my variable's in the denominator. So what I'm going to do is multiply both sides by X just to get it out of the denominator. That's really ugly. So now I have X times the sine of 61 degrees equals 2.1. And I can divide both sides by sine of 61. Now remember, this is just a number. Like sine of 30 was 1/2. This is just a number, but it's actually going to be an ugly number because 61 degrees is kind of a weird, ugly thing. So I'm going to leave it as sine of 61. And then I'm going to go to my calculator and I'm just going to type in 2.1 divided by sine of 61. And I get 2.401. I do like 3 decimal places unless it says otherwise. All right, next one, 22 degrees. The one we're looking for would be opposite that. The one we know is adjacent because this is the hypotenuse. So we are looking for the opposite. We know the adjacent. Opposite, adjacent, that's tangent. Opposite over adjacent. So since the variable's in the numerator, all I have to do is multiply both sides by 16. And I have 16, tangent 22. And so X is 6.464. Ooh, this one, I'm looking for X, but it says Y is 25. Notice I have 2 right triangles here, which makes it kind of interesting. So I've got this right triangle, which I'm going to remove. 30, and this is the Y, and it says Y is 25. So in this triangle, so this is this triangle, I could find my missing sides. Now, if you remember, 30, 60, 90s, if this side's 25, this side's going to be 50. That's nice. Or I could have used opposite over hypotenuse. I could have said the sine of 30 equals 25 over x. And then done x equals 25 divided by sine of 30, and still would have gotten 50. So this side is 50. Now I want to look at the big triangle that has x in it, which would be this one. So if I'm looking at that big one, this side was 50, this is x, this is 30. Well, now the relationship I'm looking at, this x is opposite, adjacent, that's tangent. Opposite over adjacent. So that would be 50 times the tangent of 30, and 50 tangent 30 gives me 50 square root of 3 over 3. Let's look at this next one. It's asking me to find this whole side x. Now, if this is a right triangle, so is this one. What I could do is split up each triangle and find the little side that makes up x. So I've got this one triangle here that has a 90 here and a 63 here. Then if I look at the triangle on the right, I'm just going to call this little side A, 27 degrees, and this is 90. So pause the video for a minute and see if you can find A and B, and then add them together to find x. Add them correctly, this is what you should get. All right. Now the last 3 examples are some word problems. And so we need to think about our line of sight when we're reading these word problems. So we go from our horizontal to what we're looking at. So if I'm looking at something that's above, I would be from horizontal, looking straight ahead, to what the top of that building is. This would be considered an angle of elevation because I'm looking up. Now, if I was looking at something down, I would have an angle of depression because from my line of sight straight ahead to something that's below me, I would have an angle of depression. Okay, so I have a tree that's casting a shadow of 532 feet. Okay, so I have tree, and its shadow is 532 feet. And I'm trying to find the angle of elevation. Oh, it's giving me the angle of elevation of the sun. So in other words, from the ground up to where the sun is, here's the sun, is 25.7 degrees. Angle of elevation means going from the horizontal up. And we're trying to find the height of the tree. Well, this would be a tangent because that's opposite and adjacent. Opposite over adjacent. See if you can get it before I do. I got the height of the tree was 256.034 feet. Make sure when you're doing word problems you include your units. From a 200-foot lighthouse, the angle of depression to a ship is 23 degrees. So I have this lighthouse, 200 foot. The angle of depression to a ship, that means the line of sight, straight out, horizontal is like that. Angle of depression means I'm looking down. To a ship, here's my ship. The angle of depression is 23 degrees. How far is the ship from the base of the lighthouse? So we're trying to find this distance here. Well, guess what? If this is horizontal and this is vertical, if this is 23 degrees, these two together should be 90. So 90 minus 23 gives me 67 degrees. Now this side is across from that. That's opposite. That's adjacent, which happens to be tangent again. Opposite over adjacent. And I got that that distance is 471.170 feet. Last example, and I don't know, 1.2 kind of mixed up on that page, and I didn't mean for it, but that's okay. We have a 20-foot ladder leaning against a house. Okay, so I've got my house, and there's a ladder leaning against it. So here's my ladder, and it's 20 feet. So that the angle with the ground is 72. How high does the ladder reach on the house? So we're trying to find how far from the ground the top of the ladder is. Well, if this is my angle with the ground, then H is opposite, and 20 is actually the hypotenuse. So this is sine, opposite and hypotenuse. So opposite is this. Hypotenuse is this. So I would multiply both sides by 20. And I would get that the height is 19.021 feet.